Hello there. So in this lesson, we're going to look at the last measurement in electricity that we're going to be covering in this course, which is resistance. So if you think about any experiences you've had with different straws, whether you're blowing bubbles or drinking out of them, you'll notice that a thicker straw like this one from Bubble Tea is a lot easier to blow bubbles with or drink from than this thinner one. And that's, of course, due to the cross-sectional area that allows more or less of the fluid through at a time. And so resistance in electricity is very similar. Some devices, some wires, some loads will let electricity flow through them a lot more easily, and you'd say the resistance is lower there, and others are harder for the electrons to get through, and you'd say the resistance would be higher for those items. So let's learn a little more. So remember that insulators are like extremely high resistance, like the plastic that's on this surface or the coating around these wires won't let electrons get through very easily at all. And that's the reason why we use those substances, to protect people from coming in contact with the wires inside, and to prevent the electricity from being lost, and thus it being inefficient transfer of the information. So the metal parts, of course, are your conductors, and these are very weak resistors, which means it's very easy for electrons to flow through those. There's a whole range in between as well that can govern how easily it is for the electrons to flow. So the analogy again works with straws, and you can think of it in terms of liquid or air going through the straw as being the analogy to the electrons flowing through. So the diameter of a straw, if it's bigger across, that allows more water or more air to be able to pass through a straw. And it's the same thing with metal wires. If you've got a thick wire like this, the electrons can flow pretty easily through it because there's quite a bit of area for it to pass through. If you have very thin wire, like these filaments in a light bulb, the old style light bulbs, it's very narrow and it's very hard for all the electrons to get through that as rapidly. So thickness has to do with the ability or the resistance of a wire. Another one is the length of the wire that electricity is passing through. Similar to the length of a straw, if you've ever done this, you might, if you compare different lengths of straw, if you're blowing bubbles or drinking, you'll notice that the shorter the straw, the easier it is to blow the bubbles, and the longer it is, the more you have to blow. Same thing with wires. A short wire is going to have a lot less resistance to the flow of electrons than a really long one. So the longer the wire, the more metal that the electrons will have to pass through, and the greater the resistance will be. Temperature. So for many substances, the temperature has sort of a direct relationship to the resistance. And the higher the temperature, the greater the resistance. You can kind of think of it in terms of objects that you're trying to get around. So if these are electrons that are trying to get from one end of this wire to another, and all of these atoms are perfectly still, well, then it's pretty easy for this electron to just like mosey its way in between the atoms to get to the other side. Now, when it's hotter, the atoms, of course, are going to be moving around and bumping against each other, and it makes it very difficult. It's like people trying to get through a crowded room. If you're this same electron, now you're trying to get through this crowd of atoms that are all bumping around against each other. It's harder to get through. You might go this way and like, oh, there's someone there. Oh, someone there. And it takes a while to bump along to get through to the other end of the wire. So the greater the temperature, the greater the resistance. In a circuit, oftentimes resistors are added to change the flow of electrons to be appropriate for the device that the electrons are providing energy to. LEDs require a very small amount of electrical flow. Very low current is required to get them to function. And so a resistor is a way in which you can take, say, a very fast flow of electrons through this wire and slow it down so that it's appropriate for the amount needed to get the LED to run without burning out. If you're going to add a resistor in a diagram, it's always going to be in series with the device that it's assisting or slowing down the electrons to function. And you can always show it with that ziggy-zaggy line there. So for this one, we don't even have a switch. We'll put the ziggy-zaggy line, and then we'll put the bulb, and that'll complete our circuit. So you got the resistor in series with the load. Finally, when you're calculating resistance, you can use what's called Ohm's law, and it also uses current and potential difference, or voltage, and you can work out the resistance mathematically. The neat thing about resistance, I think, is that the units are not English. It isn't an English letter that's used. It's this Greek letter omega that's used, and the unit is called an ohm. All right, so let's use Ohm's law here to solve a couple problems. The resistance of a load, given a potential difference of 9 volts and a current of 3 amps. So resistance, potential difference, and current, there it is. We want this guy, so R equals V over I. And so we got 9 volts divided by 3 amps, and that means the resistance is 3 ohms. A little rearranging here. You can always add your triangle. Let's see here. This time we're looking for voltage. So V equals R times I. And that means we have 12 ohm resistor times 4 amps, which means 48 volts. This time we're looking for the current. So what is the current? There it is there. So I equals V over R. That's 30 volts. And we're going to divide by 6 ohms. And that's going to end up producing 5.0 amps of current. Okay, hope that helped. See you soon.